Hello. Here we're going to be going over Chapter 8, which are the elimination reactions. In the second edition of the Top Hat textbook, they have combined the previous elimination chapters, which were separate. But for here, we're going to be talking about both the E1 and E2 reactions. So, elimination reactions are typically taught alongside the substitution reactions because they have they're sort of cousins in that you have an electrophile, you have another molecule that has negative character to it, and the electrophile having a leaving group which ends up leaving. The biggest difference between the substitution and the elimination reaction is that in this case the molecule with negative character is not going to act like a nucleophile, it's going to act like a base. And instead of acting directly on the carbon that has the leaving group within it, it's going to react on this adjacent one. Okay? And so it's going to react here. But the leaving group is going to leave. And what's left behind is this carbon-carbon bond, scar. Okay? So just a bit of nomenclature. The carbon that has the leaving group on it, that one is considered the alpha carbon. The beta carbon is the one that's immediately adjacent to it. Okay. If you go one further out, that would be the gamma carbon. Okay, so it's alpha, beta, gamma, alpha, beta, gamma. And if you went one further out, it would be the delta one. So I don't use that terminology very often, but I have seen it used before, so I wanted to make sure that you guys had at least seen it at some point. Okay? It's not completely foreign. But what we're going to be doing is, again, we're going to be looking at the for wherever that leaving group is. So in this case, it's the bromine, and so we're going to be looking on either side of it, on the adjacent carbons, and asking ourselves, do they have at least one CH bond? If they do, then what we can do is we can have our base remove it and form the alkene. Okay, so if we look on this side here, yep, there's a hydrogen on this side, so we can make a double bond here. So this hydroxide can come in, grab that hydrogen, and those electrons are going to collapse down. And so we can make this product here. If instead we were going to look on the other side, right? Well, there's at least one CH bond on this side. That means that we can make a double bond on the other side of the of where that leaving group is. So we're going to make it here because we're reacting between these two carbons. So you can sort of see this is where I've highlighted here. That's where the original leaving group is, and so we've reacted on one side and we've reacted on the other. Okay, because both sides had CH bonds available. If there wasn't a CH bond on one side, we couldn't do the reaction. Okay, because we need to have a base to be able to rip away the hydrogen. Okay, we'll talk about later about the exact mechanism of this because it's going to make a difference whether or not you're having an E1 or an E2, right? Just like the substitution makes a difference if it's SN1 or SN2. Okay. Now, they're not made equally. Okay, when you have these, when you have two potential products, okay, they're not necessarily made 50% one, 50% of the other. Okay? And so we can look at it here in that here is where the original leaving group is. Okay? So it's this iodine. So you look on the left, there at the CH2, we can make a double bond over here. If we look on the right, there's at least one CH on this side, so we can make a double bond on the right side. Okay, to make here. But if you notice, the majority of it is this one here. Okay, this is the major product. Most of the product is this. Okay, with just a minor amount of here. Okay, so can we predict this? Not necessarily the numbers, but we predict, this is going to be the major product, this is going to be the minor product. Okay, and it turns out we can look at alkene stability. Okay, and so when we look at this, we talk about things that are substituted. Okay, so you're looking at relative to ethylene, which is this. Okay, ethylene, which has 4 hydrogens on it. Ethylene. Oop, I can spell. Okay, here. What we're saying is, how many positions have we swapped a hydrogen for something else? Okay, so for monosubstituted, right, we've removed 1 hydrogen, but the other 3 are there. Okay, so we've substituted one of those hydrogens for something else. For disubstituted, right, there's still these 2 hydrogens. That means, 2 of the other ones have been substituted for something else. For trisubstituted, right, we've swapped out 3 of these. And for tetrasubstituted, that means we've swapped out all 4. Okay, and it turns out the more substitutions you have, the fewer the hydrogens you have on the alkene, directly on the alkene, the better. Okay, and it's what's called, and the reason why it's stabilizing this is what's called hyperconjugation, which basically means that these carbon groups here, where they have the R, they can actually kind of assist with the by providing some electron density. It's pretty subtle, but the main thing is, the more substitutions you have in the double bond, the more stable it is. The more stable, the more you're going to make it. Okay, because remember, nature's lazy; it wants to be at the lowest energy state. So in this case, right? So if you compare how many hydrogens are in that carbon, are on that carbon there, okay, on that, directly on the alkene, right, we have 2. If we look at this alkene, right, we've got 1 hydrogen here, and we got 2 hydrogens here, right? It's a little hard to see, sorry. There's 2 hydrogens here, so here we have 3. Right, so here we've had 2 substitutions, this one we've only had 1. So we want the one that has the fewer hydrogens directly on the double bond, so that's why this one is the major product. Okay. So same thing with this, right? We'll actually talk about this where we're going to make OH into a leaving group by adding some acid, but it works the same way. Okay, so we look at the we look at here, right? We look at here, and we look at here. So the red product would be this, right? Because we'd make it between here. The blue product would actually be, would put it here. So it would actually be that. But these are actually the same product. If you rotate around this right? If you rotate around that single bond, which is totally fine to do. These are actually the same product. And then the green one would be here. But if we look at this, right, so for the red one, right, there's 2 hydrogens here on this carbon. That carbon, there aren't any because there's just carbon-carbon bonds. So here you've got 2 hydrogens on it. On the green one here, no hydrogens, right? It's just 2 carbons. Here we've got 1 hydrogen, right? So this is more substituted. This has fewer hydrogens on it. So this is going to be the major product. Okay. Now, you'll see this a lot in later chapters as well, because we'll have a really nice reaction. We'll have nice rules, for how to predict, this is the product we're going to get. But somewhere along the way, a chemist asked, well, what if we wanted to make this product, right? What if we wanted to put that on the less substituted side? So how do we do that? Because this can be very useful, right, for your synthesis, and we'll talk about that in the next chapter. But it turns out that we can utilize what's called sterics. So having things big. Okay. So one of the biggest, a really large base like this, potassium T-butoxide. Okay. Notice how you've got this T-butyl group down here. It's going to have a hard time getting into here to grab that hydrogen. Okay. And so what it does instead is it says, well, I'm going to take what I can, and I'm just going to take this one because it's at the end, right? It's sticking straight out. And so we can, it's just simply easier to get to. And so for here, what ends up happening is this becomes the major product. So if you want to switch the preference, what you do is you use a really, really, really big base, okay, with a lot of carbons on it. Okay? So something like T-butoxide is a classic large base. There's some other ones that are similar to it, but what you can do then is switch it. Okay. Should say switch the preference. Okay. So here we go. So here's the first one, right? So we've got here, right? We've got here is our leaving group. Here is our base. All right. So here's the base. So we're going to look on this side, right? Well, there is a hydrogen there, so that means we can make a double bond there. Right, so I'm going to draw it up here just so we have room. So we're going to make that product. If instead we looked on this side, well, there's a hydrogen on the right side, right? So that means we can make a double bond here. Okay. So now if we look at this product here, right? We're going to look at on these carbons, right? So the left-hand carbon, there's all 4 bonds shown, so there's no hydrogens here. On this one, right, there's 3 bonds shown, so that means there's 1 hydrogen. 1 hydrogen. On the blue one, right, we're going to be looking at those 2 carbons. Now this one only has 3 bonds shown, so it must have a hydrogen. And this carbon here only has 2 bonds shown, right? Just the double bond. So that means there's a hydrogen here. There's a hydrogen here. This one has 3 hydrogens, so it only has 1 substitution. So this one is going to be the major product. If you compare these two. Now I'm going to do an extra page just so we can draw this because it gets pretty big. So okay, so now I'm going to draw the chlorine up here just for ease. Okay, and so we need to so we're looking at this carbon here. But having the carbon down here or up here, in this case, it doesn't really matter. So with that, so we're going to look over on this side, right? So well, that only has 2 bonds shown, so it must have 2 hydrogens on it. We only need 1. Okay, so that means we can make a double bond here. Now we'll talk about cis and trans in a bit. Now, right, so we also want to look down here, right, because this one's adjacent as well. This methyl group is adjacent. So there is at least 1 CH bond here, so that means we can make a double bond right there. So there's our second product. And then finally, we can also, right, so that's where the original, this has the leaving group, so now we're going to look at this one. And this carbon has 3 bonds, so there's 1 hydrogen on there, so that's fine. Okay. And so what we're going to do is we're going to make our double bond between here. Okay. And so when we look at, Okay, so we're going to look at these carbon-carbon bonds right here. So here, this carbon, it's got the one hydrogen. Over here, it's got none because it's got all 4 bonds shown. So this one has 1 hydrogen. If we look at this one, we're going to be looking here and here. The top one has all 4 bonds shown, so no hydrogens there. But this one has 2. So 2 hydrogens. Now for the green one, we're looking at here and here, and both of these actually have all 4 bonds shown. So there's actually no hydrogens there. I'm going to put this so you don't think it's an OH. Okay, so we're looking for the fewest hydrogens, the most substitutions. Okay, in this case, it's this green one here, so this will be the major product. So there we go. Now we're going to talk about the mechanism. So how do we form this? Okay. With that, so we're talk about the E1 first. So it is similar to the SN1, where the very first thing that happens for both the SN1 and for the E1 is the leaving group leaves. Okay, so for this one right here, it's the leaving group leaving. In this case, the chlorine is going to come in. Right, so here's our, here's the 2 electrons for that, and that bond here. They're both going to hop up onto this chlorine to make this 4th set of lone pair. After that, then it has a choice. Okay, so you can have you can have this act like a base, right? Remember, you have to have an adjacent hydrogen. Okay, so it's going to grab this hydrogen and these 2 electrons, right? Right, because it's going to be, right, because remember, this is a polar covalent bond. Well, actually, no, this is going to be an acidic, it's not really a polar covalent bond, but it's an acidic hydrogen, because the electron density is going to get pulled towards that positive charge, so it's going to weaken this bond, the adjacent bond, right? Because the electrons are like, hey, we're negative, there's a big positive charge over here, we're going to want to sort of lean that way. So it's going to weaken this CH bond. This guy here, right, this is definitely a polar covalent bond. It's going to see the opportunity. It's going to want to make a bond to that hydrogen. Hydrogen can only have 1 bond, so these 2 electrons are going to flip over here to make this new pi bond here. If you were to do that as an SN1, right, now this is going to end up working like a nucleophile and attack directly on that carbocation. Okay, so then you'll get substitution. You get the substitution right at the carbocation. But the base has to work next door, right? Because we have to react at both places where the leaving group is, right? That's got to leave. But then we also have to react with one next to it in order to be able to make that carbon-carbon double bond, right? So for that, you have to react at both places. Okay. So one of the classic places where you see this, okay, an E1 reaction is with the dehydration of an alcohol, and it's called a dehydration because ultimately you're going to be losing a water molecule, right? When you get dehydrated, what happens? You've lost a bunch of water, right? When a molecule gets dehydrated, it has lost a water molecule. And you'll say, wait a minute, it's an OH. How do you lose a water? Well, I'll show you. But it's still going to be, the way that you figure it out is still going to be the same, right? You look at where you were going to make this OH into a leaving group, into a good leaving group, and then you look at these beta carbons here, the ones that are immediately adjacent to it, and say, okay, we're going to make a double bond there and there and there, as long as they have at least 1 hydrogen. Okay, and you would make this, and then this would be the major because it only has, this one has 1 hydrogen, this one has 2. So that's going to be the major product. If you look at this one here, right, this is where the leaving group is, right, and you look on either side, and you can make, the one on this side is going to be the major product, and the trans is more stable than the cis, so this is actually going to be the major product. But it's going to be between these two between this double bond here. Okay. So how does this work? Well, OHs, if you remember, are really terrible leaving groups, right? Because if they were to leave, you would make an OH minus, which is a which is a really strong base, right? OH minus is a really strong base. So we want to have leaving groups be weak bases, okay? And so what we do is we have to activate it first, and for that we're going to put in a little bit of acid, right? Because remember, this is a polar covalent bond, right? This is also a polar covalent bond, right? So this oxygen is going to get attracted to the hydrogen. This hydrogen is very acidic, right? So, because it's on sulfuric acid, and so we're going to make a new bond here, and then here, this is a lone pair away from being a water molecule, right? Because remember, we think of water not as HOH or H2O, but we think of it as HOH, not H2O. Okay, and so we're a lone pair away from being water. Okay, so all it has to do is just grab these two electrons, right? Ta-da! And voila, we've got ourselves a lone pair. We've got ourselves a water molecule. Water molecule is obviously really stable because it's 2/3 of the surface of our planet. Right? And so in order to make an OH into a good leaving group, you add a little bit of an acid catalyst. Okay. So this leaves, so you right? So this water molecule leaves, right? Just like you would expect with any other sort of E1 or SN1 reaction. Okay, so we're making the second set of lone pairs here on the water, and we leave behind the carbocation intermediate, just like we did with an SN1. Okay. Now, for an E1 reaction, okay, now we have to have something come in, and it's usually easier to think of it as the conjugate base from when that hydrogen came by. So it's going to grab that hydrogen, right? Because we weaken this CH bond here because those electrons are going to get pulled towards that positive charge. Okay, and so this is going to form a bond with that hydrogen. This is going to then collapse down, and this bond, these two electrons here, are going to form that bond there. Right? These electrons here are going to form the new OH bond there, and voila, our catalyst is regenerated. Okay, but remember, we lost a hydrogen earlier, right? So we lost a water molecule earlier, so that's why it's called a dehydration. Okay, but we ultimately end up with an E1 mechanism. But OHs are really nice because they when you put in some acid, they work really well as E1. Now, the problem with E1s is the same problem we have with SN1s, in that we have a potential for rearrangement. Okay, because we have a carbocation intermediate, it will come in and it'll rearrange if it can form a more stable carbocation intermediate. Okay, so we're going to walk through this with an alcohol, but it would work with an alkyl halide as well. Okay. So, and you know that something's happening because if you look at this, right? So something's not quite right, because even if you look at these two, right? Just looking at these two, right? This one has 3 methyl groups on it. This one has 1 methyl group. If you come over here, now each one of these has 2 methyl groups on it. Oops, something must have moved around. Okay, so if you look at where the hydrogens are, where the groups are before you start the reaction, then you may be able to predict where, what's going to end up getting moved. Okay. So first thing we have to do for rearrangement, right? We need to turn this OH into a good leaving group, and the way you turn an OH, you do that with an OH, is to add a little bit of acid. So you turn a bad leaving group into a good leaving group, and then it leaves to leave behind the carbocation here. This carbocation intermediate. But for here, right, it's secondary, right, because it's got two carbons on either side of it immediately attached. However, if we shift one of these methyl groups over, and it's literally just kind of rocks over, what ends up happening is now this carbocation here is tertiary. The carbon bearing that positive charge is a tertiary carbon, right? Here, here, and here. And that's much, much, much more stable because of this hyperconjugation, which means that the neighboring carbons can kind of help out a little bit with their electrons. Okay, and so you're buying a little bit of stability with this, and then the base can come in on either side. So if you come in and grab, this hydrogen over here, you end up making this product, this alkene product. If you instead go to the other adjacent CH bond, then you would make a one on this side, right? So here's where that carbocation originally was, right? So you go on so you go on the left side and then the right side. That's where it originally was. Okay. It's not where the so remember hit the wrong button. So this is where the OH originally was, right? But that's not where we're looking because we have this rearrangement. We're looking at where the carbocation ended up. That's where you end up looking for the double bond here. Okay. So let's do an example for this. Okay. Okay. I don't know why. Okay. Okay. So let's say let's just do a really simple one. So let's just do Br plus okay. So, and this is going to be an E1 reaction. It may not necessarily seem so obvious here, but I'll show you. We're going to walk you through it. So the first thing you're going to want to do before you do any mechanism is draw on those hydrogens. Okay. So right, so CH3, CH3, H, CH2, CH2, or CH3. Same thing goes here. This may not necessarily be the best example, but we're going to walk you through it. Okay. Okay, so notice, right, here's where the double bond is. Okay, so that's obviously where things are changing. So we got methyl, methyl, CH2, CH3, methyl, methyl, CH2, CH3. Those aren't changing, but these two carbons here are the ones changing. And so what's happening is we're losing a hydrogen here, we're losing a bromine here compared to where we were over here. Okay. And so for this one, okay, so that gives us a clue as to what may be happening. Okay. You know what? I'm going to do this a little differently just because it's going to be the minor product, but it's going to show you a little bit of we're going to make this minor product plus Br minus. Shouldn't have done that. It's going to be a little bit easier to see. Okay. So here it's CH2, CH3, so yes, it's a minor product. All right, and here's a carbon. Okay. So we're actually going to be making this product here. Okay. And so if you look at where you started from to where you're going to end up, well, this CH3 and this CH2 and this CH3, this CH3, this CH2, this CH3, those are unchanged. However, these three carbons here are different, right? Notice how we lost a hydrogen here. We've lost a hydrogen here. But however, here on this carbon, we've actually added a hydrogen. Right? That seems weird for an elimination reaction, but okay, we'll go with this. Okay. So that means something has to have moved. Okay, and the most likely culprit is if this thing is gaining one. Okay, we don't have any hydrogens over here to gain, so it's probably one of these guys that has moved, right? Because these two carbons have lost one, this one has gained one, so we must have gained a hydrogen for this carbon from perhaps one of these. So let's walk through the mechanism for this. Okay, so the first thing that happens with any E1 or SN1 reaction, right, the leaving group leaves. So that's going to go, the bromine is going to go away. Okay. So, right, plus Br minus. Okay. So for this one here, right, notice how this is now, right, secondary. Okay. Actually, we don't even need this, so we don't use this. Like I said, this is a really bad example. This isn't the world's best example. Okay. So this is a secondary carbon here. Okay. So what we can do, though, is we can shift that guy over. Right? We could shift one of these hydrogens over, but that would put the carbocation here, and we're still at a secondary. Plus, we know that this CH2 doesn't change from this CH2 to that CH2. But this one does, because it goes from a CH to just a C. This CH3 that's right here is too far away. It's too far away to help. You can't break off one of these CHs and shift it way over here. It's just too far of a reach. But this one here, right next door, is fine. It's close enough to lend a hand. Okay? And so what's going to happen is, what you're going to get is this. Now that if you calculate the formal charge, now it's there. Okay. So now, I'm just going to rewrite this as a CH2. Now, this bromine can come in, grab one of these hydrogens, and that can collapse down. And this is acidic because these hydrogens are getting pulled towards that negative charge. And so when you grab that, you're going to make that product. So I'm sorry this was a little bit, so I kind of overthought this a little bit. So this is how it works. Okay, so let's walk through this again. The bromine is going to leave, right, to form the carbocation. It's a secondary carbocation, which is okay, right? But if you want to take a glance on either side, well, if I were to move it over here, it'd be a secondary carbocation. If I were to move it over here, I can make a tertiary. Aha! So let's move this hydrogen over, because that's going to be easier to move than a methyl group. Plus, it preserves the tertiary carbocation. Right? We're going to shift that hydrogen over, okay, to go here, and that makes this into a tertiary carbocation. That's when the bromine can come in, or some sort of base can come in, snatch that hydrogen. That's going to collapse down, and you're going to make the double bond between these two. Right? So we have our CH2 formed here. We've removed the hydrogen here, and we can remove that hydrogen here to leave behind a CH2. Now you can, just like with the, so for these, just like for the SN1, we can get a methyl shift, we can get a hydride shift. It doesn't really matter. It just depends on what's needed to form that triple bond. A hydride shift is going to be easier because it takes less energy to do, just because it's a lot lighter weight. But methyl groups can shift around. Now for E2 reactions, okay, this is what's analogous to an SN2, okay, and they're going to follow the Zaitsev rules. But the nice thing is you're not going to have to worry about rearrangement, okay, because remember, so just like for an SN2, it's concerted. You're not going to have that carbocation intermediate that can rearrange. Okay, so in this case, everything happens in one step. Your base comes in. So here's your leaving group here. So you're going to look next door to the adjacent carbon. It's going to grab a hydrogen. That's going to collapse down, and that's going to kick away the leaving group. Okay, so it's exactly the step. It's similar steps as what we're having in the E1. It's just how you think about them are different. Instead of the leaving group leaving and then the base comes in, here the base comes in, grabs it, and then the leaving group leaves. Okay, but you end up making essentially the same product. Okay? But it is considered, there's no reaction intermediate. So the nice thing is you don't have to worry about the about rearrangements. But you have to get this in the proper alignment, and you have to start breaking bonds. And so that's gonna cost you some energy, but it's gonna be better overall. Now, so for here, right? Here is our where our leaving group is. So we have to look on either side, right? So we look on the left side, right? There's one hydrogen here on that side. So that means we're going to have a product on that side plus Br minus plus CH3OH. We can also look on the other side. Right? There's one over here. So we can make a double bond there. Right, we can make one there. So this is going to come and grab, collapse. I forgot to do that for the other one, sorry. This is going to come in and grab, collapse, kick away. So you're going to make plus Br minus. Right, so this is where the original leaving group was, And so we're just putting on either side. So if we want to say which one's the major product, right? Again, we're going to be looking at those hydrogens, right? So hydrogen, hydrogen. So this one has 2. This one has 3 hydrogens total on that double bond. So this one's going to be the major product. Because it's more substituted, it's more stable. Zaitsev says this is it. Okay. So for here, again, if we look on the right side, right? There's a CH2 here. So that means we can make a double bond there. So this is going to come and grab a hydrogen. That's going to collapse, kick away. So you're going to make this double bond there. If instead you had there's hydrogens over here, right? So that's going to grab, collapse, kick away, and so you're going to make this product. And then for both of these, it's plus Cl minus plus H2O. Right. So for here, right. So for this top one, right, this one has 2 hydrogens on the double bond. This one also has 2 hydrogens on the double bond. So in this case, there's no preference on which one you make, because they both have 2 hydrogens. They're both disubstituted, so it doesn't matter in this case. I don't know why that would be the major. Now, one of the things that has to happen with the stereochemistry, so remember for SN2 reaction, remember you got, with the stereochemistry, you ended up getting this inversion. Well, there's a little bit of craziness, quirkiness with the E2 reactions, okay? And so it turns out that this hydrogen has to be able to be 180 degrees away from the leaving group, okay? It's what's called antiperiplanar. It's in the same plane, but it's pointed in the opposite direction, okay? So it has to be in this orientation in order to be able to work. So it's not that big of a deal if you're talking about just a regular, a regular alkane, okay? But notice how when this, so this will get extracted, that'll collapse down, this will kick away, but when that does that, okay, these two, this side and this side, compress to make the double bond. Okay, so this one and this one are here. Let me put these in different colors. So the greens will be on this side, right? And the oranges will be on this side. Okay, so if it has to, so if it grabs that hydrogen, then it's going to go there. So for here, if we're going to grab this hydrogen, it has to be in this orientation, and so these guys will be over here. All right, these guys will be over here. So it just kind of compresses it down. Okay, and so there's going to be a preference, right? Because trans is going to be more stable than cis. Okay, so it's more likely to get this hydrogen than that hydrogen. Okay. The biggest issue with this is when you have a cyclohexane. Now, the previous example we had, we're just going to, unless you're given information about if it's axial or equatorial, then you can assume that it's probably in the correct orientation. If, however, you're given that information that this one is equatorial, this one's axial, then you have to be a little more careful. Okay, because they both have to be, both the hydrogen and the leaving group both have to be axial. They have to be in this orientation, because if one of them was equatorial, is say that, you know, if you tried to grab this hydrogen, then the chlorine would have to be over here, and that's not a chlorine, that would be a carbon. So they both have to be axial, both the hydrogen that you extract and the leaving group. Okay. Now remember, if it is equatorial, if the leaving group is equatorial, then what has to happen is we then have to do a chair flip in order to get it into the correct orientation. Okay, to get that leaving group in there. And so if you want to look at these two examples, you have methyl chloride. So this is, I think it's related to menthol. Okay, I think menthol has a methyl group here. Anyway, doesn't matter. And then neomenthol, and the only difference is the orientation here. Okay, so if you look at the neomenthol, you can get it so that, right, so remember the neomenthol, this is down, right? Remember a dash is down, and then this is up, okay? For the menthol, remember this is up, down, up, okay? So we can get, so for the neomenthol, right, the chlorine is down. So if we do the chair flip so that this hydrogen, so that this leaving group is down, axial down. Okay, remember this isopropyl group is also down. Okay, so this is down, this is down. So when this is axial, this would be equatorial, which means its hydrogen is going to be axial. So we can get it between carbon 1 and carbon 2 because there's an axial hydrogen here. Now, no matter what, on carbon 3, there's always going to be an axial hydrogen. So we're going to form both products between here and here, between 1 and 2 and 2 and 3, because they both have axial hydrogens when the leaving group is axial. With the methyl chloride, however, so this is how it would want to go in the chair conformation, right? Everybody is equatorial. Okay, so this is down, that's up, that's up. So, but this one here, notice is equatorial. So we need to come in and do a chair flip. When that happens, right, remember all the axials and equatorials flip, but the ups and downs don't. Okay, so this is equatorial, it gets flipped down to, or it gets flipped to the axial. Okay, so remember this is axial. But what's axial here? Well, this is axial now, right, because the carbon-carbon bonds are pointed down, so it's pointed straight down. Okay, and then this one's the axial here. So not only do you have to put this isopropyl group in the axial position, which is terrible, and the methyl group, which is terrible. But doing so actually blocks you from going between these two carbons, right? Because now there's no longer an axial hydrogen. The only axial hydrogen there is this one here. And so the only product that can form is between carbon 2 and carbon 3 because there's no axial hydrogen here. Axial CH bond. Okay, there was never one here, so we can't make it between 1 and 2, so this is the only product. Okay, so we have to make sure that we understand when this chlorine, when our leaving group is axial, we need to look at the adjacent carbons to make sure that there's at least one, so that the adjacent one has an adjacent, or excuse me, the adjacent CH bond is also axial. If it's not, then it can't get in the correct orientation to do an E2 reaction. Okay. So that is important. So this is why we dealt with chair structures. Okay, it's because of things like this where the orientation of that axial and equatorial and up and down. It can help you predict which products are going to be formed. Okay? Now, we are going to talk about, so for these reactions, okay, we can have, it turns out that, obviously like everything else, it's never quite as easy, okay? And so if you were to do a reaction, okay, and you do it at you perform the reaction at lower temperatures, at different temperatures, you can actually get different, you should say at different temperatures, you can get different products being the major one. Okay? And so this is what's called the difference between kinetic versus thermodynamic control. Okay, so if you run this under low temperatures, okay, you're going to get what's called the kinetic product, and at higher temperatures you're going to get the thermodynamic product. And what ends up happening is the intermediate has a choice. Okay, it has two different products, or two different possibilities. One of them is a shorter hump, shorter activation energy, but it doesn't get you quite as much energy at the end, savings. Okay? The other one requires a lot more energy, but you get a lot more out. Okay? So it's sort of like if you think about scratch-off lottery tickets, right? If you buy a $1 lottery ticket, probably, what you're going to be doing is you're going to, the maximum that you can win is, I don't know, $100, which is still awesome for that. But if you buy a $10 lottery ticket, you could win $1,000, right? But it takes a lot more money to get that you have to spend a lot more in order to be able to make a lot more. So if you only have $1, or say $2, you're not going to have enough. You're not going to have enough to buy the big lottery ticket. So you're going to get the little lottery ticket, and then you earn. You're going to get. Good chance you're going to make. There's a chance you're going to make some money off of it. If I give you more money, and in this case, and just like with the molecule, if I give you more money, then you can buy the big lottery ticket and get a lot of money out. You can get a lot more money out, I should say. Okay, so that's what's going on here. If the molecules don't have enough energy to get over the big hump, then they'll go over the little hump and get a little bit, get what they can. So in order to be able to give the molecules more energy, you have to heat it up. And so that allows them to get over the higher hump and get a much bigger payout at the end. Okay, so if given enough, infinite number of times an infinite number of energy, right, it's going to want to go down here to make this 1,4 product. Okay, and so this is the thermodynamic product. Okay, if we don't have a whole lot of time, okay, and we don't have a whole lot of energy, it's going to go where it can, and so this one is considered the kinetic product because it gets there much faster, because it has a much lower activation energy to get over, right? To make this product here. So this is the one that's formed at the lower temperature is the kinetic product because it's easier to get to, but the one formed at the higher energy is the thermodynamic product. So you can use this, you can tune the temperature of your reactions to, and not all reactions can do this, but some of them can, to figure out which is going to be the major and the minor product. Okay? Assume for our reactions purposes, like predict the product, that you're going to get the thermodynamic product, the more stable of the ones. But you can play these sorts of things in the lab. Okay. Good luck.